This video is on section 7.1, double integrals. And if you look at definition 197, that looks very intimidating as far as a definition. So I want to assure you that as a general rule, when we calculate integrals, we're not going to use the definition of integral. But I want to explain that definition. And to explain that definition, I want to go back to Calc 1 and express the integral in a similar way. This is probably not the way you saw the definite integral expressed in Calc 1, but we could have used this definition had we wanted to. So remember the standard picture. We have this function from a to b, and we chop this interval up into a bunch of little intervals. I'm going to call the left endpoint a, and that's going to be x sub 0, and the right endpoint b, that's x sub n. And so we have these little xi's between a and b. And so what we want to do basically is we took a representative right here, call it an x sub I star, right? And then we looked at f. So we looked at the function value. And then essentially, if our function was positive, that's the picture I'm drawing. We look at these rectangles, we looked at the areas of these rectangles, we added them all up, and then we took the limit as the widths of these rectangles go to 0. And if that limit exists, then that was the integral. Now I'm going to express this another way. We're going to say that the function is integrable if there's this number L, and yeah, L is eventually we're going to call that the integral. But let's just say there's this number L. So L for a limit right now. And for all epsilon, there's a delta. So this is sort of limit language here. For all epsilon, there's a delta such that whenever, okay, we're going to take our x sub I and our x sub I plus 1, so we're going to take two of these next to each other, right? And that distance is going to be small. And then we pick our x sub I star out of this interval. So for all I, right here, 0 less than or equal to I less than or equal to n. So remember, that's the way we indexed our xi's. We started x sub 0, went up to x sub n. So then we pick our representative point out of that. So for all epsilon, there's this delta. So that when we pick these things small, and then we pick our representation point out of the interval, then what do? We add up the sum I equal 1 to n of x sub I, f of x sub I star came out of this interval, times the width of this interval. We have the xi plus 1 minus xi. We wanted that limit to be the integral. So how do we write that in our epsilon delta language? We have the absolute value of this minus L is less than epsilon, right? Whenever we can get these things really small. What do we mean by small? We mean that xi plus 1 minus xi is less than delta. That's what we mean. And so when that happened, we said our function was integrable, and this limit that we came up with is equal to L. Okay. So I'm going to call this video part 1. In part 2, I'm going to leave this up here, and then I'm going to draw the picture that justifies the language that's in the notes. I probably won't put the language in the notes on the video because you have the notes in front of you. I'm going to leave this up here though, and then I'm going to draw another picture. That's what I'll do in the second video.